Every day, you do something about 20,000 times without a single conscious thought. You take a breath. While we often use the terms interchangeably, breathing and respiration are distinct processes. Breathing is the physical movement of fresh air into the body and foul air out. Respiration is the chemical oxidation of food, the process your cells use to extract energy. Your body faces a constant cellular energy crisis. To produce energy in the form of ATP, your cells demand a steady supply of oxygen. This reaction generates carbon dioxide as a waste product. If that carbon dioxide builds up, it alters your blood pH, leading to symptoms that eventually result in cellular failure. Your brain manages this through the Medulla Oblongata and the Pons. These regions act as sensors, measuring the partial pressures of carbon dioxide and oxygen in your blood. They function as command centers, adjusting the depth and rate of your breathing to maintain your body's chemical balance. Every breath is a coordinated delivery and waste removal mission designed to keep your cells from failing. The journey begins with a mechanical shift. When you inhale, your diaphragm contracts and moves downward, while your external intercostal muscles lift your ribs. This diagram shows how this coordinated muscular contraction significantly expands the volume of your thoracic cavity. As the lung volume increases, the internal environment changes. The intrapulmonary pressure inside your lungs drops relative to the atmosphere outside. Because fluid moves from high to low pressure, the weight of the Earth's atmosphere physically pushes air into the lungs to equalize the difference. Lungs do not suck air inside. They are passive vessels being inflated by external atmospheric pressure. Inhaling is the result of biology using the fundamental laws of fluid dynamics to move matter. This illustration tracks the pathway the air takes. It travels through the upper respiratory system, starting at the nostrils, moving through the pharynx, and passing the larynx. From there, it travels down the trachea and enters the tracheobronchial tree, branching repeatedly into smaller bronchi deeper inside the lungs. This network contains about 150 milliliters of volume, known as the anatomical dead space, a region where no gas exchange occurs. This plumbing system filters foreign particles, humidifies the air, and warms it to body temperature to protect the delicate tissues of the lower lungs. The branching geometry of the respiratory tree exists to condition the air for the gas exchange waiting at the branch tips. The journey ends at the alveoli, millions of thin, grape-like sacs wrapped in a network of capillaries. Here, gases move by simple diffusion. Because the partial pressure of oxygen is higher in the lungs than it is in the oxygen-depleted blood, the oxygen moves across the alveolar membrane into your bloodstream. About 97% of that oxygen immediately binds to hemoglobin inside your red blood cells. The returning carbon dioxide waste travels through the blood using a more complex system. 70% travels as bicarbonate ions, 20 to 25% binds to hemoglobin, and 7% remains dissolved in the plasma. At the lungs, the blood releases this carbon dioxide. It diffuses into the alveoli, replacing the oxygen that just departed. Human survival depends on this trade occurring millions of times every single minute. The right side of this chart shows the process reversing. Expiration begins as the diaphragm and intercostal muscles relax, allowing the chest cavity to shrink. This reduction in volume increases internal pressure until it exceeds the outside atmosphere. This higher pressure forces the carbon dioxide-rich air back up the respiratory tree and out of the body. The physical act of breathing is the essential mechanical servant to the chemical act of respiration. Take a deep, conscious breath. In one motion, you just used atmospheric pressure to fuel a chemical trade. It is a process you repeat with every second of your life.